Hello everyone and welcome back to another set of lectures and as part of the course Digital System Design. In this set of lectures we are going to look a little bit deeper into one aspect of sequential circuit modeling in Verilog, in particular the concept of finite state machines. So let's look into FSMs or finite state machines a little bit deeper. First things first, what is a finite state machine? At a very high level, it's a digital circuit that moves between a fixed set of states, right. So this part, the fixed set of states, is essentially what finite state refers to, right. And what do we mean by move between states? The state of a system is defined by the values that are taken by the registers that are present in the circuit, right. And therefore, for one given set of values, let's say I have 3 registers and they have the values 0, 0 and 0, I would consider that one state of the system. If those same registers had the values 0, 0 and 1 in that particular order, then I would consider that to be another state of the system, and so on, right. So with 3 such registers, obviously I could have a maximum of up to 8 states. Now once I have a circuit that basically can exist in one of these states, the next question that arises is, okay, how does a circuit move or transition from one state to another? And that in general is a combination of the present state of the system and the inputs that are provided to the system. So this part of it is already something that you would be familiar with from the basic circuit on digital introduction to digital systems. What we are going to do here is to go a little bit deeper into how such states or state machines could be implemented in practice, and in particular look into how we would do that in SystemVerilog. Okay, so we can think of the core building blocks or rather finite state machines make an appearance as core building blocks for a number of digital control systems, right. For example, the UART, the serial receiver transmitter circuit, I2C and SPI communication protocols that you would be familiar with from the course on embedded systems. In general, a lot of interface controllers such as things that are used for configuring memory, displays, sensors and so on. And in general, any kind of system sequencer, something where you want to take your system or circuit through a sequence of different transitions. All of these are places where a finite state machine is a suitable kind of controller that could be used and makes an appearance in such circuits. So there are a few key components that we would like to that we need to know the terminology for. The first is of course the states of the system, right. And by states we are essentially talking about different possible configurations of the system. As I said, the state is determined by the values stored in each of the individual registers that are present inside the system, and we can think of these as different configurations of the system. Now there are transitions or ways by which we can move from one state to another. So that's another important concept. How do we define these transitions? And of course we have inputs as well as outputs, because after all this is a digital circuit, right, and we would like to do something useful with it. Now what we are going to do is sort of take an example out here. This is a relatively simple example, an elevator, a lift controller or elevator controller, just to be clear, the essentially means the same thing. I'll be using this as an example to sort of illustrate the different kinds by which we might be able to implement code, and later on we'll go a little bit deeper into one specific example of a finite state machine that could be implemented as in order to solve a specific kind of problem. So now let's think about what kind of functionality we might expect from a lift controller, right. The first thing is, I mean, I'm going to assume that we are all familiar with how a lift or rather the external functioning of a lift. What I mean by that is the user interface. What is it that the user sees in terms of how a lift operates, and then we want to translate that into how we could implement a digital circuit that achieves that functionality. So the first thing we can assume is that there must be one state in which the lift is idle, right, meaning that it is stationary at a given floor and waiting for inputs. Now obviously there are two other states that we can straight away think about. One is where the lift is moving up, the other where it is moving down. And then we also have this condition where the lift has stopped but is not yet idle, right. So, the difference between the stopped state and the idle state is something that we will see a little bit later as we sort of refine the functionality expected of the elevator. Lift and elevator, I am going to use the words interchangeably over here. Now, let us think about it. How do we generally interact with the lift controls? As a user, we would have an up button and a down button, which in general are what are called the call buttons for the lift, right. Typically, the convention is that if we want to go to a floor that is higher than the one that we are on, we press the up button, right, irrespective of where the lift is. The lift might by itself be either above us or below us, but it does not matter. What you are supposed to indicate is the direction in which you want to go. Now, once you have pressed either the up button or the down button, that should get recorded by the lift controller in order to decide what it needs to do. And there is probably, as far as the lift is concerned, going to be a certain input, a logic input, which tells it whether it has reached the target floor. Now, how would we do this? There would probably be sensors embedded somewhere in the doors or in the lift control, which tell it how far it has reached. In other words, where is it aligned? This could be a light based sensor, it could be a proximity switch, it could actually be a physical kind of a switch that gets activated when the lift reaches a certain location, right. All of these are different ways, but the point is this is not really an input that is received directly from the user. Similarly, there are a couple of other inputs, door closed and door opened, which are position sensors, which once again are wired into the lift and not something that the user provides, but need to be operational and actually provide inputs to this finite state machine that we are going to build, or the controller that we are going to build. And there are a couple of other inputs which are sort of indirectly related to the up button and down button that we have, which are basically called the up pending and down pending controls. What that means is that while the lift was in motion, somebody has pressed a request to either go up or to go down, and based on that, since the lift is not going to stop suddenly as soon as somebody presses a button, or we do not want it to stop immediately, we want it to respond to the previous request only when it has actually stopped and probably gone into an idle state. Now, all of these are the inputs to your lift. As you can see, only these two are user visible. The rest of them are things that are generated internally but are nevertheless important for the functioning of the lift. And then we have certain outputs. In particular, there is a motor up and a motor down, which would activate whether the lift is going up or down. There is a signal to open the door, and there is also a signal which usually is some kind of an indicator that the lift is available for new calls, right. You can call it either up or down. Now, this is a simplified model of a lift. You are very likely to find that modern lifts actually have more functionality. There could be alarms, there could be like safety setup such that in case there is a loss of power, it automatically needs to roll to the nearest floor. A few different inputs of that sort, but this captures the basic essence of what is actually going to happen. Now, one other thing to keep in mind is modern lifts are almost certainly not controlled by hardwired digital control circuits like this, right, or like what we are going to design. What is almost certain to happen in practice instead is that this finite state machine is going to get implemented as a software solution on most likely a microcontroller. Now, the reason for that is because the rates of input and output data that we are dealing with over here are sufficiently slow that a microcontroller can do a great job of handling everything. At the same time, the microcontroller also gives a lot more flexibility in terms of what you can and cannot do with such a system. But that does not matter. The basic idea of having a state machine and being able to implement it would be very similar in terms of how you would go about designing it, even if you were doing a software implementation. Only the implementation details, right, of how you would actually go about building the system itself would differ. And we are going to use this as an illustrative example that tells us how, if we chose to build a hardwired circuit for it, we could go about doing it. The fact that there might be other better solutions is besides the point over here, because we are using it as an illustrative example. So, this diagram over here is typically what we have in mind when we talk about a finite state machine transition diagram, right. And this is in some sense a graphical representation of everything that we discussed on the previous slide, right. As you can see, there are 4 states over here, and the states are essentially indicated by these circles, large circles in this case, right. So there are 4 states. There is an idle state, there is a moving up state, there is a moving down state, and there is a stopped state, right. So exactly the same as what we had out here: idle, moving up, moving down, and stopped. Now every single arrow that you see over here is a state transition, right, and the writing that you find next to that arrow, right, in some cases it could be confusing. Potentially you might ask, is this writing corresponding to this arrow or to this arrow? But in most cases hopefully it is sufficiently clear. Especially for something like this, it could potentially be confusing about whether it refers to this or this, but given the fact that there is something else written over here, hopefully it should be clear that this door closed and down pending actually refers to the lower arrow out here, right. If not, it just means you have done a bad job of drawing the diagram. It's not something fundamentally a problem with the state diagram, it's a state machine itself, right. We just need to find a better way of drawing it. So let's go through this and try and understand what these state transitions actually imply, because what you actually see over here is a much better defined set of transitions which have basically taken the concepts that we had in the previous slide and converted them into more or less mathematical equations. So let's look at this. Let's assume that we are initially in the idle state. The rest of what you see out here is essentially the outputs of the system, right. And if we look at it, what we have over here is, for example, when we are in the idle state, we can define a few things. One is that the doors should be open, and the simplest way to indicate that is that you can have the doors signal, right, which is probably going to be a Boolean signal of some kind, can be set to 1 to indicate that it is in the open state, or you might have an explicit doors open signal to indicate that something has to happen which actually pushes the doors into an open state. Similarly, the motor is expected to be off while we are in the idle state, because idle literally means you are not moving. And also the ready signal becomes equal to 1. This is probably used as some kind of an indicator to show that the lift is stationary and ready to be called to some other floor. So these, in other words, what you have out here are the outputs of the system. One of the things that you can notice over here is these outputs depend only on the state in which you are, right. This is actually a choice that we have made. We will talk a little bit more about it later. Now let's look at this transition where we go from the idle state to the moving up state. What are the conditions under which that would happen? One is that the user must have pressed the up button, the door must be closed, and we are not already at the target floor, right. So of course the question becomes, how do we define each of these? Door closed is just a switch, some kind of a sensor that indicates whether the door is closed or not. The at target floor is once again a Boolean value which is picked up based on maybe a comparator which checks the floor number we are currently on versus the floor number that we are expected to go to, and from that it decides whether we are at the target floor or not. So rather than complicating it and saying that check the floor number and so on, we assume that that has got abstracted out into a signal that says whether or not we are at the target floor. And if you look at this logic, it's very straightforward and easy to understand. If we are not at the target floor and the door is currently closed and the up button is active, we should start moving up. Similarly, if we are not at the target floor and the doors are closed and the down button has been pressed, we should start moving down. Now already you might notice that there is a possible problem out here, right. The problem simply says, what if both the up button and the down button have been pressed at the same time, right, because both these conditions in that case are satisfied, but clearly the lift can only be either in the moving up state or in the moving down state. It cannot be in both of them at the same time, right? And in such cases we usually need to take some kind of arbitrary decision which says that this is a priority, maybe up has a higher priority than down, right, and therefore we just choose one or the other. There is no wrong decision here. In other words, the wrong decision would only be if we tried to activate both the moving up and moving down states at the same time, which depending on how you have actually written your state machine is most likely impossible to do in the first place, right. So this is a possible race condition, so to say. If you have both of them getting activated at the same time, then it's not clear into which of the final states you would end up. This is part of the problem of concurrency that we need to deal with when we are dealing with digital hardware systems. For that matter, even in software something like this could happen. And of course, as I said, the solution is simply to pick one and go with it and come up with a solution. Alright, I am not going to go through every single state over here in full detail, but roughly what you can see is while you are in the moving up state, the doors must be closed. The motor up is going to be 1, so that the motor is actually running in such a way that it pulls the lift upwards, and the ready signal goes to 0, which basically indicates to the rest of the world that the lift is currently moving and therefore it is unlikely to respond to any calls that you have. Now you might wonder why exactly is a ready signal required over here. That's partly to sort of keep track of, and it could be used for other purposes, like for example an indicator light which says whether or not the lift is idle and ready to move. Now let us say that we are moving up and we have reached the target floor. In other words, the at target floor got activated. We move into the stopped state where a couple of things happen. One is the doors are set to the open state, the motor is turned off, so you are not moving anymore. Now of course you could argue that it should happen in the other order, the motor should be turned off and then the doors should be opened. The point is, the reason why it was written in this way was sort of to indicate that as far as hardware is concerned, it only depends on the state. What we are writing in here is not necessarily a sequence in which these things are going to happen, right? What we are saying is that all of these things need to happen when we are in this state, and presumably they happen concurrently at the same time, right? So that you turn off the motor and you also activate the door opening circuitry at the same time, right? Now if you wanted those to happen one after the other clearly, it is quite possible that you might actually end up adding some more circuitry or another state to the system in order to achieve that kind of functionality. Now you will notice also that the ready over here is equal to 0, which basically tells you that the idle state, right, the doors open, motor off, stop state, doors open, motor off, there is a difference in that the ready is 0 in this case and the ready is 1 in this case. Now why would such a thing happen? Because basically what would normally happen in the stopped state is that you are waiting for the doors to be open and for people to get out. After that the doors start closing, and only when they are closed are you actually basically ready to move, right? You could also argue in the idle state, should the doors be open or should they be closed, right? And that sort of, once again, what it's actually telling you is that you probably need some additional states over here where the lift is idle and a person hits an enter button and therefore the lift door needs to open so that they can actually enter the place, right? Now how exactly we design it, right? We probably need to add some more states or some more functionality. That depends on the user requirements. As I said, this is a simplified version of what we would like to see. Now from the stopped state you have a couple of options, right? If once again the door is closed and there is an up pending signal. Now where is the up pending come from? While it was moving up, let's say that somebody pressed an up button again, that would get recorded as an up pending signal somewhere in the memory of the circuit, right? And therefore it would start moving up again. On the other hand, if there was a down pending signal, it might move into the moving down state, right? In other words, from the stopped state, it doesn't really go into idle necessarily. It might just decide that, okay, after having opened the doors, the next thing that it looks at is that it needs to again start moving down or moving up if there was another call waiting for it. On the other hand, if there are no pending calls, go back into the idle state and wait over there for something to call you, right? So this is how you interpret a FSM diagram, the finite state machine, right? And what we are interested in over here is, for other complicated systems, how do we go about defining and then actually building or implementing a circuit that will give us the functionality that we want. Now there are a couple of different types of ways by which finite state machines can be implemented, particularly with regard to the outputs, okay, and those are essentially called Moore versus Mealy machines, named after the people who came up with the two different kinds of machines essentially. Now a Moore machine essentially says that the outputs depend only on the current state, right? So what do we mean when we say that the outputs depend only on the current state? For example, in this diagram that is shown over here, these are the outputs and they depend only on the current state. So, this is an example of a Moore machine, right. In this case, basically what it says is that the door open command depends only on whether it is in the idle or in the stopped state. It does not look at any of the other inputs such as the up or down or up pending or any of the other signals that you might have over there, right. If you are in this state, then the door open command will be activated. That is essentially what a Moore machine says. A Mealy machine, on the other hand, could depend on the current state as well as on certain inputs, right. Now, an example of that would be, let us say you had an emergency stop requirement for the lift, right, and that basically says that somebody should be able to press the emergency button and the lift just comes to a stop. It overrides any of the other inputs that we have. It cannot wait for the system to go into some kind of a stopped state and then respond, right. It cannot wait until it gets out of the moving up or moving down state. It has to pretty much immediately start responding and move to another state, right. Or it could be an alarm button, which basically says that as soon as I press this, the alarm needs to get triggered, right. It does not need to wait until I have come to a stop and the doors have opened. The alarm should immediately get triggered. Or it could be something even as simple as a light or a fan, right, which does not really depend on whether you are moving up or moving down. You do not want to change a state just for that. It is something which just literally, the output, even if you are moving up and you turn on the fan, it should basically turn on. So, there are a couple of different scenarios where Mealy machines might be the right way to go. However, Moore machines tend to be more predictable, because after all you can precisely say that if you are in a given state, these are the outputs that you are going to see. The other good thing from a circuit point of view, and this will become more evident when we actually get to implementing these things, is that you do not have combinational paths directly from input to output of a system. And this can actually be quite valuable for high speed circuits. For something like an elevator controller, it probably does not matter, but for high speed circuits it does, because having combinational paths from inputs to outputs can actually significantly affect the speed at which a circuit can work. This also means that it is easier to cross clock domains, and what that means is, because many of these FSMs are used as controllers for other kinds of circuits, over here what we are saying is everything over here is handled by a single clock. You do not have to also worry about the inputs coming in at a different clock speed or being synchronized to a different clock, and therefore transitioning somewhere in the middle of a state. So, in general, for control signals such as motors, actuators and so on, it is preferable to have this kind of a Moore machine. Mealy machines are, in general, they respond faster to inputs. In many cases, it also turns out that a Mealy machine can be implemented with fewer states than a Moore machine can, right? And this potentially has the has an impact that it could actually respond faster in some cases. It essentially, as soon as an input changes, you have the ability to try and have the output also respond, whereas a Moore machine first needs to move into the target state and only then it can change its outputs. So, that can result both in fewer states as well as quicker responses. Mealy machines therefore tend to have lower latency even for protocols, including things like FIFO buffers, first in first out buffers that are used for transferring data between two digital circuit blocks and so on. Now, the point is, it is also possible to have some kind of a hybrid between the two, where the majority of your outputs essentially are in the Moore form, where they depend only on the state, whereas some of them could have Mealy kind of behavior where they are able to respond quicker. Typically, you would ideally, I guess, just call that a Mealy machine in some sense, because as long as it has the dependency on current inputs, you could argue that it is a Mealy machine. But the fact that many of the outputs have a Moore type of behavior can also be quite useful in certain scenarios. So, to just summarize that again, especially in the context of FPGAs, right, which we will be looking at a lot throughout this course, Moore machines map well to registered outputs, because when you are in a given state is when your outputs are also going to transition, and therefore you can make sure that along with the state transition the outputs also get registered, meaning that they are actually changing at the edge of the clock and therefore are stable throughout the entire clock period. Mealy machines have a problem that way. There is a possibility that because of the way that the input can influence the output, timing analysis can become more complicated. In particular, you can have input to output combinational paths. So, you may also need additional output registers to meet the timing requirements of your circuit. which means that in practice very often a hybrid approach is suitable, right. Critical control signals you would probably prefer to have as more outputs, whereas certain things such as the status flags and emergency stops and so on are more likely to be Mealy outputs. Now, one other factor with regard to how the states in a finite state machine can be encoded. The simple way of looking at it would be to say that if I had, let us say, n states, what is the minimum number of flip-flops that I would need in order to be able to encode those n states? And the way to look at it is, let us say that I have some k flip-flops. Right. So, I have, let us say, F1, F2 up to Fk, right. This essentially indicates k flip-flops in my circuit. What that means is that I could have 0, 0 up to all ones, right, which is basically 2 to the power of k different combinations, right. Another way of saying it is, if I had n states, I need to make sure that 2 to the power of k is greater than or equal to n, or you can rewrite that to say that k must be greater than or equal to log n to base 2, and since k must be an integer, we can basically take the ceiling function, which basically converts it to the nearest integer that is larger than this value log n to base 2. So, therefore, if I say that you require n states, it is fairly straightforward to calculate what is the minimum number of such flip-flops that is required in order to encode the states, right. And this is very often done. This is usually done in the context of what is, the binary encoding, where we could pretty much just say that, okay, if I have 4 states, I will just encode them as 0, 0, 0, 1, 1, 0, 1, 1. If I had 5, I would go with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 and 1, 0, 0, and the remaining 3 states, remaining 3 possible numbers are just not used, okay. So, what that means is, with log n to base 2 as the maximum number of such flip-flops, I should be able to implement this circuit. Now, there is another way of encoding state machines where we can sort of look at transitions, right. We sort of say, okay, what if I have a sequence of transitions that goes something like this, right, where I tend to have a chain of operations one after the other. Here what I would say is, the sequential operation would basically say 0, 0, 0, 1, 1, 0, 1, 1, and what you can see over here is 2 bits are changing, right. The 0, 1 is changing to 1, 0. Now, is that necessarily a bad thing? Well, we would like to avoid it for a couple of reasons. One is that there is more switching activity here, but a more important one, especially if you have some kind of Mealy outputs or even more output in this case, right. As you transition over here, since you have 2 different bits that are being changed, there is a possibility of something called a glitch, which is a temporary but unwanted transition happening in the output, right. So, glitches, especially in sort of critical control systems, can be problematic. Therefore, we would like to minimize the possibility that such a transition or a scenario can arise. The alternative is to say what's called use what's called a gray code, right. And over here what we say is we have 0, 0, that goes to 0, 1. Now, from 0, 1 we go to 1, 1, which means only 1 bit transitions. And what do we do from there? From there we can go to 1, 0, again only 1 bit transitions, right. In many cases it is possible to have an explicit gray code definition in this form that allows us to transition 1 bit at a time. In some cases it may not be possible. Now, the next possibility that we have is essentially what's called a one-hot encoding, right. And the one-hot encoding basically says, look, if I have k flip-flops, I will just use F1 to be 1 and all the other flip-flops to be 0 to indicate that I am in state 1. When I go to state 2, I will make F1 as 0, F2 as 1 and everything else to be 0. If I want to move to state 3, I will make F1 and F2 as zeros, F3 will become 1 and everything else will become 0 again. In any given point, only one of the bits is going to be non-zero, every other bit is going to be 0. Now, what is the potential advantage of that? The advantage is actually decoding complexity, because now remember that in order to generate the outputs corresponding to a state, I need to know which state I am in, and based on the logic of which state I am in, I am then going to write some Boolean equations that tell me what my outputs are supposed to be, right. Now, if I had an output state encoding which is multiple bits like this, I would need to effectively have a decoder which tells me that I am in this current state, and therefore I have some other signal that basically activates and says, okay, I am in this state, therefore these outputs should become equal to 1. Whereas with a one-hot encoding, this is essentially the one-hot encoding that I talked about, where only one of the flip-flops has a non-zero value, that decoding is almost trivial. It is trivial in fact, right? When you have literally only one of the signals as non-zero, you can basically combine just OR those states together and say, if I want, for example, the elevator up button, the motor up button to be active, it should be in this condition where it's in the moving up state, right? But there might be some other signal which is basically in multiple different states, right? And if that signal would essentially be done as an OR of the different states in which such a scenario could have arisen. So the decoding part of it becomes extremely straightforward. Now, of course, the obvious problem with it is, rather than having log n registers, I am actually talking about n registers, right? It turns out that FPGAs are very rich in registers. By the very nature of their fabric, it turns out that the ratio of registers to combinational logic is high in FPGAs, whereas in ASIC design, application specific integrated circuit design, registers tend to be expensive. They occupy area, and therefore we do not just have the luxury of putting in as many registers as we would like. So one-hot encoding actually tends to be a lot more common in FPGAs. Having said that, it is also possible to come up with hybrid kind of encodings where we end up with some number between n and log n, and we choose that in such a way that it sort of minimizes our decoding complexity, but at the same time giving us some of the benefits of what you might get by one-hot encoding. So maybe a partial decoding is already done. Now, the interesting thing is, how do we do this as designers, right? And the point is that you have probably come across ways by which the state assignments can be optimized, right? In practice, when you are actually writing finite state machines for implementation in Verilog, you leave that to the synthesis tool, right? The tools are extremely good at exploring different kinds of FSM state assignments, and even if you just sort of give some arbitrary assignment, almost certainly it's going to get re-encoded by the synthesis tool. So rather than trying to make a decision on whether you should go with sequential or gray encoding or one-hot encoding, it's better to just go ahead and write it out using maybe sequential encoding, and you will almost certainly find that the synthesis tool actually in most cases re-encodes the state representations for you in such a way that it optimizes some aspect of the circuit implementation.